Okay, let's talk about PLCs, or programmable logic controllers. First question, what is a PLC? Well, programmable logic controller probably sounds an awful lot like a computer. It is. It's basically just a specialized computer that's made for industrial and commercial applications, or even if you get a little PLC on a chip, for controlling your washing machine. The difference between PLCs and other general purpose computers is that the PLC has a lot of input-output capability. It'll directly read voltages, directly read digital inputs, switch inputs, and it'll directly control outputs either on-off or pulse width modulated and things like that. So this is an example here from Unitronics. It's a V350 PLC. There's nothing really special about it, but this one has a nice display on here, and it's got some buttons we can use for user input, and I've got just a real simple display that I can press F1, there's a label here, I press F1 that sets start, and F2 is stop, and the others don't do anything. It's nothing special, but we'll be programming this stuff ourselves in a bit. But what does make the PLC special is the input-output. If I look at the back, it has a module that they're called snap-in I/O modules, because there's different versions. But it has a module back here with there's 15 connectors on this side and 15 connectors on this side. And if we run down the list here, these first two connectors are labeled here. This is the 24 volts in, 0 volts. This is a ground. Going across here from pin 15 through pin 4 are the digital inputs, and if you look here, they're labeled I0, I1, I2, I3 for digital input 0, digital input 1, 2, 3, etc. And it's important to note those numbers, because those numbers are going to be the numbers you're going to want to refer to when you do the programming. So this wire here is going into digital input 0, so I know that when whatever I would hook to this wire, I can read it through the input 0. It's got some high-speed inputs that are piggybacked on top of these. Again, there's 3 high-speed inputs, so if you choose high-speed inputs, which use a pair of these, you can't use these as general inputs. Analog inputs, analog 0, analog 1, again these are piggybacked, so you're going to have to make a decision, do you want digital or analog inputs. Outputs, there is a set of relay outputs. The relay outputs use a pair of pins, and they will handle up to, I'm sorry, I'm going to have to read this, my memory isn't the best, 30 volts DC, 250 volts AC, 5 amps. Okay, so they're fairly capable outputs, and then there's some other outputs that are lower current capacity out here, and these will also do high-speed outputs if you want to do pulse width modulation, things like that. So that's the big difference between this and a general computer, is all these inputs and outputs. And beyond this, we can plug into the side here, there's an expansion port, and we can put additional input-output modules. So we can control a lot of physical things. We can control motors, we can control other mechanical relays, we can get inputs from switches and buttons and sensors and things like that. So that's why a PLC, and I don't know what I did, the display just went away, but okay. Probably a bad connection here on the power. Okay, that's PLCs. We'll talk about getting them programmed and getting them set up in just a minute. So let's talk a little bit about the history of PLCs and how they came about and why we use them, and more specifically why we use the ladder logic program that we're going to be seeing in just a little bit. If we go way back to the Stone Age, before everything was computer controlled, we still had machine processes, we still had fairly complex assembly lines, things like that. That came before computers. And to control those things, we used what was called relay logic, where you wired it up. You'd get an electrician to wire up a system using relays and buttons and switches and create the logic that made things turn on and off when you wanted to, using limit switches and relays and things like that. And it was all hardwired. And I have a simple example here on the board. Let's assume that I want to control a motor here, and this motor, we'll say it runs some kind of press. So when we turn the motor on, the press comes down and stamps apart and comes back up, okay? I've got a lot of controls I want to use to control that motor. Somewhere I'm going to have an emergency stop button so that somebody not working right at the machine sees something goes wrong, they slap the button, shuts everything down. There's a button I'm going to push to enable the machine, get things started. At the end of the day, there's a button to push stop, which just shuts everything off. And to make the machine cycle, I want to push a button to make the machine come down, stamp my part, and go back up, okay? One problem is, with these kind of machines, especially in the old style stuff where you didn't have proximity sensors and light beams that you interrupt, the problem was that an operator can be putting a part into the machine and push the button at the same time and not get their hand out in time, and there were just a lot of one-handed press operators out there. It's human nature. It's a boring job. It drags on all day. Sometimes you're paid piecework prices, so you're trying to get it done fast. You get careless. So one thing that people came up with, well, let's have two buttons, so the operator has to push two buttons to cycle the machine, and then that makes sure that they don't have their hand in the press at the time they push the button. And that worked until somebody figured out you could take a broomstick and push the two buttons with a broomstick at the same time that you're feeding the parts in, and then you have a lot of one-handed press operators. There's a lot of other systems, but that is something to remember if you're working in industrial systems and working with these PLCs. Keep in mind, how can people interact with your system? How do you keep them safe while they're interacting? How do you keep people out of contacting moving parts? But that's not the focus of this class. That could be a whole class in itself. So anyhow, what we have is we have two buttons here, one left, one right, and when those buttons get pushed, the machine cycles. So here we are, it's 1952, and we don't have a computer, so we're going to hardwire something up, okay? Well, I'm going to use a couple of relays, R1 and R2, in conjunction with these switches, and let's walk through how this works. Here I have a low voltage plus, excuse me, and a low voltage minus. Those are low voltage rails, and as I connect things up, I complete a circuit from one rail to the other, and current will flow when I complete that circuit. So if I take power from this rail and I run it to my emergency stop switch, this is a normally closed switch. If I push it, it opens, okay? So normally it's closed and current will flow, and that's fine. And I run along here to my start switch. My start switch is normally open. So if I push that start switch, it closes this circuit and current flows, and it flows through the normally closed stop switch there, and it flows through this relay and to my other rail, okay? Well, as the current flows in the relay, it's got a pair of contacts on it. This contact closes, okay? So when I push the start switch, this will energize my relay, this will close. Now the current will flow through here if necessary. So now when I open the start switch, I actually have a closed connection from here through that closed connector, back to there, through the relay, into there, okay? So the current keeps flowing, and as long as the current keeps flowing, this relay stays closed, so I've essentially latched this circuit, okay? I push this momentarily, it latches that relay, and it closes both of these contacts. Now if I want to stop the machine, I press the stop button, and that opens the circuit right there, and with that circuit open, no current flows through the relay. This relay opens here, and that relay opens there, and then even once I let go of that stop button, and let it close again, I still have an open circuit because this is open and that's open. Okay? So I've got a start and a stop to run this circuit. So once I've pressed the start, I've energized this relay, I've closed this relay contact up here as well. Okay? So that relay goes to the rail, comes from the rail, and here's my two normally open push buttons, left and right. When I push both of those buttons, push and hold both of those, that closes this, that energizes this relay, and that relay closes these two connectors. These two connectors are connected to the 440 volt high voltage, high power rails, okay, and the motor will turn and the press will cycle. If I let go of these in the middle of the cycle, the motor shuts off, everything stops. And if I hit the stop button here or the e-stop there, again, everything shuts off because I open this relay. Once this relay is open, there's no power to that relay. That relay opens, the motor stops. Okay? So that's how you would have done it in the old days. And this would have been done by an electrician. You would have drawn up a schematic, labeling everything you wanted. And electricians are trained and understand schematics. And there's my eraser. I knew I had one somewhere. And you could build it, and and it worked fine. The problem is if you wanted to make any change to this logic, okay, perhaps once you start this cycle, you want it to complete, or perhaps once the motor gets to the bottom of the cycle, or almost to the bottom of the cycle, you want it to complete. You don't want it to get stuck halfway down. Suppose the operator's using a broomstick to press this. He's got his hand in the press, and the press comes down on his hand and cuts it off, and his crushed hand is in the press, and he's going to let go of those buttons, and the press is going to stay there, right? Perhaps you want the press to go back up, How do you do that? Well, that's a rewiring process. It's, expensive, and this is a simple example, but if you have a whole assembly line with a lot of machines, these, changing the logic between a set of connected machines gets expensive and difficult, and sometimes you have to get pretty creative with these relays and things like that. So there's got to be a better way, right? Faster, cheaper, simpler. That's what engineers do. They make things faster, they make things better, they make things cheaper, they make them more functional. And the answer is a computerized device like a programmable logic controller, and where we can program this sequence of events, okay, with these inputs. So then the next question is, what kind of language do you use? We could program it, well, back in the 50s it would have been Fortran, right? Nowadays we could program it in C. But the problem is you've got a whole army of electricians and machine operators that grew up and were trained with this logic, okay, and they understand this. Do you want to retrain everybody, or do you come up with a logic system that all those people can understand? So back in the 50s and 60s, they came up with ladder logic, where it's a graphical language, and it looks like a circuit diagram to a certain extent, and makes it easy to understand for all those electricians that have been trained on relay logic to understand. Of course, time has gone by. Most of the guys that did the actual relay logic have retired, and we don't have to worry about them anymore. But the problem is the whole new generation of machine operators were trained in ladder logic, so we can't change from ladder logic to something else because everybody's trained on ladder logic. And it'll never change, ever. It'll just always be here. So what would this look like in ladder logic? Well, we would have a rail, a pair of rails in our ladder logic diagram. And in my ladder logic, I'm going to have a normally closed connector, which is my e-stop. And that feeds this stop-start. I have a normally open connector and a normally closed connector. This is start and stop. And those control a relay coil, which we'll call R1. and R1 is a parameter in memory, or an operand in memory. These could be triggered by an external input. This could be an external input where it just senses an external voltage going high or low and triggers this. These could be buttons on our PLC, or they could be buttons somewhere else. And that controls relay 1. Then I have another ladder here where I have a connector, which is, oh, I didn't finish drawing this one. Okay, so I need this latch function, right? So if I put a connector here, and I make that R1, so when this is energized, that's closed, and I put it around this, then I have this stuff here in blue done like that, okay? And we'll switch to green because I did this circuit in green. So this is green. I've got this relay connector here, so I just put in a connector, R1. Obviously there's no need for a physical connection. It just references the same memory parameter that I'm setting and clearing through this connector coil. I have two normally open connectors. One is left and one is right. And this goes to another coil. We'll call this R2. Okay? And R2 will go directly to, will specifically control a output. So we'll have an output labeled R2. And that will actually trigger the physical relay. The PLC may or may not be able to directly handle the 440 AC or whatever it is. You may have to actually have a separate relay to control the high current. Some PLCs may have that high current capability. The one we're looking at right now doesn't. Okay, so that's my ladder logic, and you can see it follows pretty much like this circuit, so that the electricians that were trained on circuits in the 50s can understand it relatively simply, and then the newer guys that have been trained on ladder logic, and they typically get trained and they show how it works just like the relays, they'll understand it as well. So that's why we have ladder logic, and it works. Obviously some things, we can do things in a computer that you can't easily do with relays. So the ladder logic concept has kind of been extended beyond simple contacts and coils, and you can put a block in here that's, a PID controller and auto tune, and it's a stupid place to put it in a diagram here, but I'm just, for some lack of a better place. So there's other functions you can put in here that are much beyond the simple logic, and it gets kind of weird because you're trying to squeeze it into this circuit diagram kind of illustration. But it works, and that's what's out there. And as a robotics engineer, if you ever end up in an industrial setting, you're going to have to be familiar with this because you'll see it all day long. Okay, so here is an actual relay. This isn't an industrial relay, this is an automotive relay, but I thought I'd dig it out just for the sake of talking about it. We've got a couple of connections here on the back, this one and this one, that connect to this coil of wire. When current flows across these two, obviously you create a magnetic field within those windings, and when you create the magnetic field, hopefully you can see this, it pulls this top piece down. Okay, let's see if I can line that up so that you should be able to see that moving. And that top piece is connected to this bottom connector, and then under here, it's hard to keep this in the screen, there's actually a connection under here, so as I push this down, and the light doesn't look like the light really shows it, as you push this down, it makes a connection between here and that bit of metal there, which is this connector. So when this is down, these two outputs are connected, and the net result is these two outputs create a magnetic field, and they can operate on a fairly low current, and they control these two outputs like a switch, and that can control a much higher current or higher voltage than you would have had available here. So that's how a relay operates in general. Now in our examples on the board, we had essentially a relay with two sets of contacts. That's the same concept. You would have just stacked another little actuator on top and get the same thing. So those are relays. Now we'll get back to PLCs.